Alright, so we're doing parametrics, and the reason that we're doing the... Ow, cat, darn it. The reason we're doing that today is to look at polar equations. Alright, so polar is another coordinate system, and eventually you'll turn that into both spherical and cylindrical coordinates. So let's go ahead and get started. As soon as I get this cat off my shoulder. Come on, computer. Alright. Come on, you. Get down here. I gotta work. Alright. So, parametric equations are typically a pair of equations that all depend on another variable. So x as a function of t and y as a function of t is our typical setup. And in order to plot something like that, we've really got to change it so that we get just a function of y equals some function of x. And to do that, we can do a few things. We can plot it by doing a table of values, or we can eliminate the parameter. So the first example here is t cubed plus 1 and y equals t minus 2. Okay? Is that focused? Okay. So the first problem said plot this using a table of values. So I'm going to choose a value for t, and I'm going to solve for a value of x and y. Now typically t is greater than or equal to 0, and the reason for that is t is typically representative of time. Doesn't have to be, but most of the time it is representative of time. And so it doesn't make sense to go back in time, right, to have negative time. So let's start at 0 and do 1, 2, 3, and maybe 4. Actually, 4 is going to be a little big. Let's not do that one. Okay, so when I plug in 0, 0 cubed plus 1, well, that's just 1. And for y, if I plug in 0, I get negative 2. Plug in 1 for both. 1 cubed plus 1 is 2. 1 minus 2 is negative 1. Plug in 2. 2 cubed is 8 plus 1, 9. 2 minus 2, 0. 3 cubes, 27, so this is 28, and this is 1. So if I want to plot that in the x, y plane, okay, so when x is 1, y is negative 2. When x is 2, y is negative 1. When x is 9, it's 0. doing this sort of thing. So what I wanted to do was to show you how to do that on your calculator as well. So if you go to your calculator and you go to math, I'm sorry, you go to mode. Let's see if I can see this. I am on mode. It's not focusing, maybe because of my face. There we go. See the mode under the fourth option, function? I moved over one, and that's PAR for parametric. And I selected that one. Okay. So once you put it into parametric, it knows that you're going to put in, if you go to y equals, you'll see it tells you to put in an x and a y equation. And I already have them in there. So t cubed plus 1 and t minus 2. And if I made my window standard, I'm going to go ahead and change it to x starting at 0, because we don't need negative x's here. And I'm also going to change my y values from negative 10 to 10 to, I don't know, minus 4 to 4 or something like that, or maybe to 2. Just make it a little clearer. So that's what your equation should look like. So again, you see that it stops because there's no zeros allowed, or anything beyond 0. We can have 0, just not negatives. So we can do that by hand, we can do it with the calculator. And effectively what we've done is we've taken these two paired equations and turned them into a set, or we took the set of equations and turned them into a Cartesian equation. So one place you might recognize this from, and I'm looking around because I'm thinking I might have had an example in a textbook, but I don't see my book. So a place where you would see something like this is in physics, right? You could have the x position versus time graph. You could have the y position versus time graph. And you can have an x versus y graph. So you can have, or you could have velocity for these, right? So the one that's position, say we had a object that's got a parabolic motion, right? So in the xy coordinate system, it would just look like a parabola. What about in the y and the x? Anybody have an idea what it looks like in those? So I see the x would be a straight line. Would it have any slope, or would it have zero slope? So let's think about it for just a second. What happens to the velocity of an object in the x direction? There should be no acceleration, right? Which means constant velocity, which means the position graph would look like some kind of line, right? So as time goes on, the position in x doesn't stay the same, it's got to grow. And the y position increases and then decreases again, so it actually looks just like the y and x graph. So that's not super important. I just wanted to, give an example of where you might see this sort of thing. And like I said, the intent for this class is to translate this into polar coordinates. So the next task that we're going to take on is to eliminate the parameter. So instead of graphing it, we can try and put the two equations together to solve for a function of y equals x, or x plus y equals something. So x equals t here, y equals t squared minus 1, and this is over an interval of 0 to 8. And I'll show you why that's important here in a second. So eliminating the parameter. Somehow I want to get rid of t and I want to have y equals a function of x. Well, this one's really easy because x is equivalent to t, which means I can just substitute it in. Right, this is just y equals x squared minus 1. So that's our equation. They ask us to plot it and give a direction. So someone in yesterday's class said, okay, well that's great, but where's the time? Like, what was the point of that? Well, time is going to be reflected in the direction. So this, we know, is a parabola that's been shifted down 1 unit, and I only get to start at 0, so it's just going to look like this. And I have to indicate a direction on my graph, so I have to put little arrows on the graph to show which way it's moving through time. So x and t are directly related. So as x goes bigger, so does time. So that is my indicated direction. So I just put little arrows there. Now that one's pretty easy. This next one's not so bad. They give us x equals e to the t, y equals e to the minus t, and this is over 0 to infinity. Right? It just says t greater than or equal to 0. So I've seen some people kind of struggle with this one a little bit. The first thing I decided to do was change this into 1 over e to the t. And so now if x is equal to e to the t, this should be clear that this is equal to 1 over x. So the equation is y equals 1 over x. We can plot that quite easily. That should look something like this. And we have to indicate direction again as x increases, or as t increases, so does x. So it looks like we'd be going this direction, right? So those aren't so bad. Are you guys okay so far? Okay. So these, we were substituting x in, right? In this case, that's not a good choice. I've got x equal 3 sine squared t. I could solve that for t and try to plug it into this one, but then I'd have cosine squared of the arc sine, and it'd be a mess. So there has to be some other way. I'll pose it to you. Do you see something that you could do here? The Pythagorean theorem. Not kidding. It was probably the program with the typing and everything into the chat. So yeah, Pythagorean theorem, right? We've got the sine squared plus cosine squared. Right, it's the Pythagorean identity that comes from the unit circle. So if instead I added these two things together, and factored out a 3, right, so I just said let's do x plus y on this side and these two things on the other, right? Factored out the 3, and sine squared plus cosine squared is 1. So I get an equation for a line, 3 minus x. And yes, I agree that this is quite a strange way to represent a line, but it works. So plotting this guy, there would be 2 points where it would touch. So we're going from 0 to 2 pi. If I let t equal 0, then what do I get for x and y? Well, sine of 0 is 0, and cosine of 0 is 1. Squared is still 1, and then multiplied by 3. So I get the 0.03. So that would be right here. This is my starting point. Let's try pi over 2. Right, I'm doing this because I have to indicate direction. So pi over 2, this one is going to be 3, and this one's going to be 0. So I went from here at 0, pi over 2 put me down there. Okay, so I'm heading that way. But then I still got to get to 2 pi, right? Well, what if I plug in pi? I'm guessing I might be off the screen. Nope, nope, just barely on there. Okay, so if I plug in pi, what do I get? Well, sine is 0, cosine is -1, but squared makes it 1. So we're back at 0, 3. I'm back up here. So this actually bounces back and forth. Does that make sense to you? And if you're questioning it, look at the equations we started with. Right, these things are sines and cosines. Sines and cosines, when they're squared, bounce back and forth between 0 and 1. So this guy is going to bounce back and forth as well. It's going to oscillate just like the equations that we started with. So yeah, good job. Alright, so we've got a few more of these. And we're going to use the same concept here for these next couple ones. So this time I've got x equals sine t, y equals cosine t. So very close to what I had before, but they're just the function itself, not squared. And again, from 0 to 2 pi. Okay. So over there, we used the Pythagorean identity. So I think I need to do that again. But to do that, I have to square both of these. So x squared is going to be sine squared. And if I add that to y squared, that would be cosine squared. Well, sine squared plus cosine squared is just 1. So I get x squared plus y squared equals 1. What is that the equation of? All right, it's a circle. In fact, that's the unit circle, right? So then the only thing we have to do is indicate direction. So when I plug in 0 into these things, all right, so when t is 0, I get 0, 1. So I start there. T is pi over 2. I get 1, 0, so I'm down here. And we should know that to go all the way around, we would do 2 pi. So no funny business here. We just have one direction. Appears we're going clockwise. Okay. All right. So the next one is 2 sine t and y equal 3 cosine t. So this looks a lot like the other ones, except that if I were to try to use the Pythagorean identity right away, it's going to cause some problems because I would get 4 sine squared and 9 cosine squared. And in order to get 1 out of them, I got to have the same amount. So with this one, the very first thing you should do is divide this one by 2 on both sides, and this one by 3. Then you can go ahead and square both sides. And add them together. And once again, that's 1. Do you recognize this equation? I find it interesting that you say an oval. Right? The shape of an oval is actually an egg, which is not the same on both sides. Right, so this is an ellipse. With a radius of 3 in the y direction and a radius of 2 in the x direction. Not the greatest drawing in the world, but an ellipse anyway. And again, we had x equal, or x related to sine, y related to cosine. So it's going to go around clockwise again. So any questions about any of those, how to eliminate the parameter, what we're doing, how we're doing it, why we're doing it, any of those things? Okay. So the next topic is obviously how do we use this in calculus, right? So we've got the, let me make sure I'm on the screen here. The derivative of y with respect to x is going to be the derivative of y with respect to t over the derivative of x with respect to t. I'm a little bit off there. Shrink this down. There we go. So dy dt over dx dt. And if you flip and multiplied that, you could see that it would look like dy dx. So this is first derivative, and the second derivative d squared y dx squared, and that is equal to the derivative with respect to t of dy dx over dx dt. Okay. So first we're going to be asked to find the derivatives and then go ahead and use them. Right, so what good are the first and second derivatives? Well, if you recall back to Calc 1, we can do increasing and decreasing, and we can do concave up and concave down. So for each parametric equation, do the following. It says, find the equation of the tangent line at the given value of t. Find where the graph has horizontal and vertical tangents. So x equals t squared minus 3. Y equals t to the fourth plus t. And at t equal -1. So this is a case where, right, we're not depending on time. If so, we couldn't have negative numbers. Actually, let's just go ahead and change this. Let's make it +1. And the reason for that is if you tried to plot this function on your calculator to look and see where that point would cross, the calculator restricts t, so let's go ahead and just do 1. See what happens. All right, so we've got to find the first derivative. So dy dx is equal to dy dt. So derivative of y here is 4t cubed plus 1. And the derivative of x with respect to t is 2t. So that's our first derivative. If we want the slope for t equal 1, we just plug 1 in. So 1 cubed is 1, times 4 is 4, plus 1 is 5, and 2 times 1 is 2. So we get the slope is 5/2. Then we need the x and y coordinates. So x is equal to, when we plug 1 in, looks like -2. And y is equal to 2. So then using point slope, we have y minus 2 equals 5/2 times x plus 2. So y equals 5/2 x. When I multiply these two, then I'm going to get 5, and move the 2 over, it'll be 7. So that should be the equation of the tangent line for t equal 1, or at the point -2, 2. It says then find where the graph has horizontal and vertical tangents. Well, we have to have our derivative right here. For tangents, right, for a horizontal one, we need the slope to be 0, which means that the numerator should be 0. So for horizontal, we're looking for 4t cubed plus 1 to be 0. That would occur at that value of t. And if you wanted you could find x, right? So the value of x there is this to the 2/3 minus 3. So that's horizontal. And if we want to find vertical tangents, that would be when the denominator is 0. So 2t equals 0, or t is 0, and x at that point is -3. Okay. So not a whole lot of new stuff. We just have a new formula, and we just have to plug in all these pieces using our basic calculus, our algebra, right? Finding our equation of a line, and then just doing some solving of algebra for the horizontal and vertical tangents. So I think I'm going to leave B for you. So what I was discussing with the other section was you guys should be done with all of your quizzes, and so I have to give you something for all those Mathematica assignments. So I'm going to give you a couple problems from Parametric and Polar on a sheet, and I'll probably give that to you over the weekend, or at least a portion of it, so that we can go ahead and get some points for that as well. So I'll leave that problem there as one of those problems. So the next part says, determine the intervals for which the parametric functions given are increasing and decreasing and concave up and concave down. Okay. So this time we are given, it's square root of t, so I'm just going to write as t to the 1/2. And y equals 1/4 times t squared minus 4. So dy dx, we need the derivative of y with respect to t on top. So that would be 1/4 times 2t, or t over 2. And the derivative of x would be 1/2 t to the minus 1/2. So the halves would cancel. And t divided by t to the minus 1/2 is going to be t to the 3/2. So that is my first derivative, which means I can find increasing and decreasing by solving that for t equals 0. So I set this to 0, and the only value I get is 0. So that would be my critical value. And if we restrict t from going beyond 0, then I just need to check a number on the right-hand side. So I'll do something like 1. So we plug in 1 into the derivative. 1 to the 3/2 is still positive, so everything is positive. And it makes sense that we have to restrict t, specifically in this case, right? We've got t to the 1/2 up here. We're not allowed to plug negative numbers into that. So t can't be negative. It has to be greater than 0. So maybe we could just make a note. So if that's positive, that means increasing over the entire interval. So increasing from 0 to infinity. And now we want to do the second derivative because we want to know concave up and concave down. So it says for the second derivative, take the derivative with respect to t of the first derivative and divide that by dx dt, which was 1/2 t to the minus 1/2. So the derivative of t to the 3/2, that's 3/2 t to the 1/2 over 1/2 t to the minus 1/2. 3/2 divided by 1/2 reduces to 3, and t to the 1/2 divided by t to the minus 1/2, right? You would subtract the lower one, and so that would be t, right? 1/2 plus 1/2, basically. So second derivative is just 3t. All right, so it's not as simple as just bringing that down. So 3t for the second derivative, which means set it to 0. You get t equals 0 yet again. We can't go beyond that anyway. So we just need a single test point. I choose 1 because it's easy. Plug 1 in there. 3 times 1 is also positive. So if we get positive on that side, it's always concave up. So it turns out this is just increasing in concave up over its entire range. Everybody still good? Any questions? Okay. So I have 2 more examples for you. And this is using something that we did kind of midway through the semester. We calculated the arc length for functions. Well, we can do this in parametric as well. And the equation is just a little different. So, let me erase this here. I'll give you the equation. So arc length is the integral from some a to b square root. Before we used to have 1 plus f prime quantity squared. But now we've got dx dt squared plus dy dt squared dt. And if you do some manipulation there, you can see that this is the same equation just for a parametric. So let's try it out. We've got an example here. It says find the arc length when x equals 3 plus 3t squared. Y equals 4 plus 2t cubed. And at, over 0 to 1. Okay? So I just got to find the derivatives, plug them in, and integrate. So my arc length is equal to integral from 0 to 1, because those are the bounds that I was given. Square root, dt out there. Derivative of x with respect to t, you bring that 2 down, you get 6t. But we got to square the whole thing. And add to it the derivative of y, quantity squared. So you bring the 3 down here, and this would be 6t squared, all squared. So that is 36t squared plus 36t to the 4th. They both have a 36t squared in common, so I'm going to pull that out. (36t squared from 36t squared is 1. And if I take it from 36t to the 4th, I have t squared left. So 36t squared, that's a perfect square. Right, that's the quantity 6t all squared. So this can come out of the radical, but still inside of the integral as a 6t. And that integral is not as bad as it looks. Right, at first appearance, it looks like we might have to do a trig sub. But instead, we can just say, let u equal 1 plus t squared, and du is 2t dt. Well, I've got a 6 out here. I can break that up into a 2 times 3. And that's fine. So this is now 3 integral. The square root becomes square root of u, and 2t dt becomes du. And we can also change our bounds while we're here. So when t is 0, plug it in there and you get 1. And when t is 1, we get 2. So we're now integrating from 1 to 2. And we don't have to change back to t. So this is 3 times. Integrating u to the 1/2, you would add 1 to it, which is 3/2. Divide by that number. So it would look like that. Cancel those. That's 2 times 2 to the 3/2 minus 1. And really the best you can write that is this, I believe. So let's go ahead and do the last example. And then of course, after I finish recording, if you guys have any other questions, you're welcome to ask. And again, this isn't this shouldn't be anything new to you, right? We've done this equation twice already in this course in different forms. And that was basic U substitution, which you should have done at the end of Calc 1 and started this class with. All right. This time we've got x equal e to the t plus e to the minus t. Y is equal to 5 minus 2t, and our bounds are 0 to 3. So once again, 0 to 3. Take the derivatives, plug them in. So dx dt, all right, that's e to the t, and this is going to be minus e to the minus t. Quantity squared, right, that's the derivative of x squared, plus derivative of y is negative 2. So I'm going to go ahead and square all this out. So this is going to be e to the 2t. I'd multiply these two together, which would be minus. You would add the exponents. So t plus a negative t is going to be 0. And you always do times 2. And then the final term squared is going to be plus, and it's going to be 2 of those. And then over here we're going to get plus 4. E to the 0 is 1. So we have 4 minus 2 here. Right? And that would just give us plus 2. So I'm going to put that in the middle. And my reason for that is because I want you to see that this is the exact same thing as down there, but now it's a plus. And so if it's a plus 2 instead of a minus 2, well then this could factor just like this, but with a plus sign. And then if we have the square root of something squared, those go away. And that's an easy integral at that point. Right? We all love e to the t because of how simple it is. So if I integrate e to the t, I get e to the t. And integral of e to the minus t is minus e to the t. And this is all evaluated from 0 to 3. So e cubed minus e to the minus 3 minus plugging in the lower bound, which is e to the 0 minus e to the 0. So that's going to be 0 there. And you just have this. So it's e cubed minus 1 over e cubed. Or you could leave it this way as well, it doesn't matter. So that would conclude all of parametric equations. Or do you have any questions? Okay. So if you don't have any questions, I'm going to stop the recording.